Greetings, Earth scientists. In my previous video, we started to talk about the model of the solar system, and in particular, we talked about the heliocentric and the geocentric models of the solar system. The geocentric model was the original model, which had Earth at the center of the solar system with the sun and the other planets revolving around it, and it was based on the idea of apparent motion. So if I look up in the sky over the course of the day, it appears that the sun is moving from one point to another, and then it appears easy to conclude that yes, the sun is orbiting the Earth. All right. In the heliocentric model, however, that movement of the sun was explained by the rotation of the Earth on its own axis. All right. This was a product of inertia after the Big Bang. So the Big Bang sent planets and all other celestial bodies or bodies in the universe spinning on a certain axis relative to their shape. And so that is what explained the apparent movement of the sun. But what explains the seasons and the fact that our, I guess, relative distance to the other planets and the sun seems to change throughout the course of a year or one revolution is the fact that it's actually the Earth and the other planets that are revolving around the sun. Today, we're going to talk a little bit more about the shape in which they revolve. If you recall, Johannes Kepler is a famous astronomer who's responsible for helping us understand that no, we don't travel around the sun in a perfect circle. In fact, we travel in an elliptical shape. So this is part of our Unit 9 on astronomy, and it's day 11. And the focus question is, how can you calculate the eccentricity of an ellipse? All right. And so an ellipse is something like a flattened circle. If we look at this picture, we see something that looks a little bit like a circle, but it's almost like we took the sides of the circle and stretched them out a little bit. And that's what we have as an ellipse, all right? And the thing we need to understand about an ellipse is that when we have one, we can identify two focal points, in this case, F1 and F2, and the sum of their distances from any point on the edge of the ellipse will always be the same. So for example, I measured this distance to the edge right there from F1, and that the distance from F2 to the same point, the sum of those distances so F1 and F plus F2 is fixed for all points on an ellipse. All right. So if I drew arrows to those 2 points, the sum of their distances would be the same if I drew as the sum if I drew it the distance from F1 and F2 to these 2 points. All right. So that's how we make the shape of an ellipse. And if you wanted to make one yourself, you'd put 2 pins in paper, stretch a string around them, maybe make like have like a string shaped like a circle, put the string under the pins, and then you could put a pencil in the string and you could just draw an ellipse around like that, which is described in this video right here, that video, and this one as well. So I want to just do some quick practice on making these measurements and figuring these things out. So if we're calculating the focal distance, we're calculating the distance between F1 and F2. Now this might feel a little bit janky. What I'm going to do is I'm going to share my whole screen so you can see this online ruler, and we're going to practice calculating the eccentricity, and then we'll do it with one more problem. So now you should be able to see my entire screen. Minimize that. All right, and now you can find these online rulers everywhere. So normally in Earth science, we'd be doing this with a physical piece of paper and a ruler. However, what we're going to do is I'm going to use zoom tools to make an accurate measurement of the focal distance. So what I'm going to do is I'm going to draw lines between these 2 points in order to ensure that my ruler sorry, is accurately set up. So check it out. I'm just going to draw a line right here, exactly on here, and going straight vertically down. And then I will draw another one at F2. And now I'm going to move my ruler into this area and set it on 0. And we have a focal distance of roughly 2.2 centimeters. All right. So that's what I'm going to put right here, 2.2 centimeters. Now to calculate the eccentricity, we have to divide that focal distance by what we call the length of the major axis. All right. And so I have that. So I'm going to move this ruler out of the way. And I'm going to erase these lines. And so the major axis is this entire length right here. I'm going to draw it with a blue line. So if I go all the way from the long side, the oblong side of the ellipse, through the focal points to the other side exactly, I have the length here. And once again, let me take red lines. I know that's ever so slightly off. No matter, we will get a very decent estimate as to the length of the major axis by taking points at the oblong ends and checking them out on this ruler. Undo that last one. And now let's set this up so this is on 0, and I have about 6.6. All right. And so if I know that the eccentricity is the focal distance divided by the length of the major axis, I have 2.2 divided by 6.6, which ends up equaling, I'm just going to calculate it really quickly, roughly 1/3. So I'm going to take that to 3 decimal places, 0.333. All right. No units for eccentricity because we have a length on top in centimeters and a length on bottom in centimeters. So the centimeters cancel out and we just get a constant. So eccentricity is a constant with no units. If we want to compare this eccentricity, the eccentricity of this ellipse, which is basically how stretched out it is, how kind of like smushed and stretched it is. Okay, the more eccentric it is, the more kind of like long and thin the ellipse will be. If we want to compare it to the ellipse or the eccentricity of Mars's orbit, what we have to do, I'm going to clear this. We have 0.333, and I'm going to check out the reference table. So if we go to the reference table, we have that definition of eccentricity if you forget it. And if we go down to page 15, we can see that the eccentricity of Mars is 0.093. So all of the eccentricities of the orbits of the planets are far less than what we just calculated. The closest is Mercury, which is the closest to the sun, and that is the most eccentric orbit. All of the other ones are so tiny that they're getting to the point where it's a much more circular shape because we're dividing a much smaller focal distance by a much larger major axis. And the closer the focal distance, or the narrower the focal distance is, the more circle-like our ellipse is going to become. One final problem we'll take a look at, and this is from a past Regents. If we want to get the approximate eccentricity of this ellipse, again, I need to find the focal distance. So I'm going to draw 2 lines down here. Make them in red, yeah. One from the star. Undo, I'm going to take that, try to take that right in the center of that star. One from F2. And while I'm at it, I'm going to draw vertical lines at the oblong ends of my ellipse so that I can also get a quick measurement on my major axis. So first I'll line this up, this ruler, so that I can see the distance between the focal points, one of which is the star, as it says in the question. The star and F2 are the foci. So The length of the foci looks like is 3.2. I'm gonna write that down here. Focal distance, 3.2 centimeters. And then major axis, I need to line this up again. Now with this side at 0, this side of the major axis, and I have about 5.6. So I'm going to go back here, say 5.6 centimeters. And now when I divide those, my eccentricity has to be those numbers divided, 3.2 divided by 5.6, which is going to equal, I'm going to calculate it here, 0.571. Okay, so now I can take a look at my answer choices. Ooh, and it seems to be right in between. Let me double check these measurements one more time. Ah, I see the problem. Actually, the focal distance between the star and F2 is 3.7. And I think I mistook it for 3.2 because I wasn't looking at my ruler very accurately. So you have to be very careful about these things. Let me adjust that, 3.7. And then let me just double check my other one to make sure I didn't also make a mistake there. That is right about 5.6. So that one looks okay. But as you can see, it's very easy to make little mistakes here. We're doing a reading, and I'm going to double check my answer again, or I'm going to recalculate my answer, 3.7 divided by 5.6, and that is actually 0.66. So let me edit and adjust this answer. There we go. And so now I'm going to move this out of the way, and I'm going to erase these lines. 0.66 is closest in magnitude to this answer right here, 0.68. So again, eccentricity is a measure of how oblong or stretched and squished an ellipse is. The smaller the value is, the more circle-like the rotation is, or sorry, the revolution is. And when we talk about the revolution of the planets around the sun, they tend to be more circular in nature. If we want to calculate the eccentricity, we have to take the distance between the focal points, in this case a star and F2, and we have to take that distance and divide it by the distance of the major axis, which is the long side of the ellipse. In other words, the oblong ends. All right. In this case, we got 0.68. I hope that was a helpful introduction. Again, Johannes Kepler, with his first law of motion, that the planets travel around the sun in elliptical motion, is responsible for helping us understand this and helping us calculate accurately the motion of celestial bodies. I hope this video has been helpful to you, and I will see you soon.